All right, so today we're going to figure out how to solve some of these limits analytically. So that means no table, no graph. We're just going to do some algebra. All right, there's a bunch of limit properties. All right, they're all listed right here. I'm not going to go through each and every one. I'll refer back to this as we do our examples so you can see. I will say I don't love the way that they have written these. It's a more concise way to write it, so it could fit all in a nice little box here, but I don't think it really conveys what's going on. So I'm going to kind of have us rewrite this first one, and then just know that this same idea applies to everything. All right, so what this says is that the limit as x approaches c of f of x is equal to L, and the limit as x approaches c of g of x is equal to M. And so if you have the limit as x approaches c of f of x plus g of x, so all of that's inside the limit problem, then you can do just L, which is this limit, plus M, which is this limit. Okay, so what that means is that you can separate this into two different limit problems. Okay, so instead of writing it as L plus M, just write it like this: the limit as x approaches c of f of x plus the limit as x approaches c of g of x. You can just split it up at that plus sign. That works for all four of the basic operations. So you can do that with subtraction, you can do that with multiplication, you can do that with division. Just have to make sure with division that limit of the denominator is not equal to 0, because then you'd be dividing by 0, and that's a problem. All right, the constant multiple rule. You can basically, what this is saying is you can do k, that constant, multiplied by the limit of f of x. So in essence, what that means is we can just pull the constant out of the problem. So k multiplied by the limit as x approaches c of f of x. And that's going to be the exact same thing. So if you ever have a constant on the inside, you can just pull that out and put it in front on the outside. All right, also something that's not on here is the limit of a constant. So if you have the limit, so let me write a title here, limit of constant. So if you have the limit as x approaches c of k, that's equal to k. So the limit of a constant is equal to a constant. Is equal to that constant. All right, I'll write out here, k is constant. Okay, so if you ever have just a constant on the inside, then that is what the limit is, that number, whatever it is. All right, power rule. This is just saying that if you have the limit of a function raised to a power, it's equal to the whole limit raised to that power. So see how like f of x is being raised to r over s? Well, instead we could write it as the limit as x approaches c of f of x, all raised to the r over s power, like that. All right, then limit of a composite is, so limit of f of g of x. You can take that outside function and pull the limit inside. So you do f of, you take the limit of g of x, and then you do f of that value. So that would be f of L in this case. All right, so let's try some examples. We'll refer back to this whole list as we go. Okay, so first problem, we have f of x is x minus 5, g of x is x squared. So first problem, we do limit as x approaches 1 of f of x. Okay, so your first line of defense on a limit problem is plug the number in. Okay, so I'm going to rewrite it with the x minus 5 in there. Limit as x approaches 1, parentheses, x minus 5, just to signify everything's inside the limit there. All right, you plug in 1. 1 minus 5 is negative 4. So if you plug the number in and you get an answer, you're done. That's all you have to do. That's called direct substitution. That is your first option every time. You should do direct substitution every single time you do a problem. And the only time you're going to run into any issues is if you get a 0 over 0. All right, there may be another time where you might get like 1 over 0, or maybe even an infinity somewhere. All right, I'm going to have to pause. I'll come back. All right, so next problem, we have the limit as x approaches 5 of g of x. I want us to get into the habit of circling what our limit is approaching. I didn't do it in the last problem either. There we go. All right, and g of x is our function, so I'm going to rewrite this as the limit as x approaches 5 of g of x, which is x squared. Again, this is a direct substitution problem. You're just going to plug that 5 in. 5 squared is equal to 25, and you're done. All right, now we have a composite function, limit as x approaches 1 of g of f of x. So we're going to apply our composite rule, where we can take that outside function and we're going to pull the limit inside that outside function. Okay, so this is going to be g of the limit as x approaches 1 of f of x. All right, and again, where x is approaching 1. Hey, what I want y'all to be thinking about is like, what, for every problem that you encounter, think about what is one step that I can do. Okay, because there's going to be problems that are really hard, have a lot of words in it, but there's always one thing that everybody can do. All right, and usually if you can identify that first thing, then you'll remember, oh yeah, I do this next, and then oh yeah, I do this next. So if you kind of identify that starting step, so that's what I'm trying to give you here. With the limit problem, circle that number. What is x approaching? All right, and then after you remember, okay, this is my number that x is approaching, what can I do with that number? All right, and then you go from there. Okay, so with finishing up this problem, we are going to evaluate this limit, the limit as x approaches 1 of f of x. So once again, I'm going to rewrite this. With my f of x in there. Okay, and so we can evaluate this limit with direct substitution. We're going to plug in the 1. 1 minus 5 is negative 4. So we had already done that one up here. So this becomes g of negative 4. All right, and then that now it's no longer a limit problem. This is just a function evaluation. This is your x value, plug it in. So this is equal to negative 4 squared, and negative 4 squared is positive 16. So that's how you can handle a composite function. Pull that limit inside the two functions where you're kind of splitting them up. Evaluate the limit, then evaluate the function, and you're there. All right, so here are 3 more. I think you should definitely try the first one on your own. All right, and then these are really just unit circle answers, which we've been practicing. But if you don't feel confident in those, you can go ahead and watch the video without trying it on your own. But if you feel confident, try all 3 first, and then unpause your video and see how you did. Okay, so once again, this is just going to be a direct substitution. We have the limit as x approaches 2. So I'm going to be plugging 2 in. 3 times 2 squared minus 5 times 2 plus 1. All right, so that is 4 times 3 is 12. 5 times 2 is 10 plus 1. 12 minus 10 is 2 plus 1 is 3. All right, this is also a direct substitution, the limit as x approaches 5. So we get cosine of 5 pi over 6. All right, so evaluating this, 5 pi over 6 is in quadrant 2. I know cosine is negative in quadrant 2. And then I know cosine is equal to square root of 3 over 2 at the pi over 6 location. So it's going to be negative square root of 3 over 2. All right, next one, we have the limit as x approaches pi over 4. So we end up with tan of 7 pi over 4. All right, that is in quadrant 4. So I know tangent is sine divided by cosine, and sine and cosine have different signs. So sine is positive. Actually, sine is negative. Cosine is positive. So a negative divided by a positive is a negative. So tangent is going to be negative in quadrant 4. And then also know that sine and cosine have the same value, same magnitude at pi over 4, at all the pi over 4 locations. They're both square root of 2 over 2. So if I do square root of 2 over 2 divided by square root of 2 over 2, I get 1. They cancel each other out. So this is just going to be a negative 1 right there. All right, so what happens if we can't evaluate by direct substitution? All right, then we're going to use some algebra techniques. So you'll see some problems that might look a little familiar that we've done with our numerical method in our previous lesson. And you'll see some new problems as well. All right, so remember, you're always going to try direct substitution first. So you get the limit as x approaches negative 3. So you get negative 3 squared plus negative 3 minus 6 divided by negative 3 plus 3. All right, and so that is 9 minus 3 minus 6, which is a 0. And this is negative 3 plus 3. which is also a 0. All right. Oh, no. Okay, so remember, 0 over 0 means we have more work to do. All right, so we're not going to do this with a graph. We're not going to do it with a table. We're going to figure this out algebraically. All right. So one thing about these problems with 0 over 0 is the AP exam does not like you to say that this limit is equal to 0 over 0, which is exactly what I did. Okay, so instead of putting an equal sign right here, I'm going to draw an arrow. Okay, and what they really want to see is that you do this. Figure out where to write this. You say the limit as x approaches negative 3 of just the numerator, x squared plus x minus 6 is equal to 0. And then the limit as x approaches negative 3 of x plus 3 is equal to 0. So you show that they're both equal to 0, and then you know that that's an indeterminate form. Okay, and so the way that we evaluate this is we do some algebra. So this one we're going to be able to factor. So we're going to turn this into the limit as x approaches negative 3 of x plus 3 times x minus 2 divided by x plus 3. And you can see that the x plus 3's are going to be able to cancel out. And so this is equal to the limit as x approaches negative 3 of x minus 2. Now we can do direct substitution. Plug in negative 3. Negative 3 minus 2 is equal to negative 5. All right, so all of these are going to kind of follow that same format. I'm not going to write each limit separately like this. That's really for a later lesson that we're going to cover second semester, even like really towards the end of the year. So I'm not too worried about that right now, but I just wanted y'all to be aware that you should never say this equals 0 over 0, because that is technically not correct. It has an answer. This limit, like our previous one, this limit is equal to negative 5. Okay, it's not equal to 0 over 0. So just be careful about that. Don't say it's equal to 0 over 0. All right, so we're going to do that step in our head. The limit as x approaches 4. Okay, if I plug in 4, 4 minus 3 is 1. Square root of 1 is 1. 1 minus 1 is 0. 4 minus 4 is 0. So it's a 0 over 0, which means we have more work to do. Anytime you see a square root, you're going to multiply top and bottom by the conjugate. Square root of x minus 3 plus 1. Same thing down here. Square root of x minus 3 plus 1. The plus 1 instead of the minus 1. That's what makes it the conjugate. All right, so we get the limit as x approaches 4. Okay, so when you multiply conjugates together, you do a squared minus b squared. So if I square this first thing, the square root cancels out, and I get x minus 3. And then minus, and then square this number, 1 squared is still 1. On the denominator, you never want to multiply, and you'll see why in just a second. So leave it as x minus 4 times x minus 3 plus 1. Okay, so here it is. This is the reason why you don't want to actually multiply down there, because this is x minus 4. I'm just going to cross that out there. And now I have x minus 4 on top. I have x minus 4 on bottom. Those cancel out. So now I have the limit as x approaches 4 of 1 divided by the square root of x minus 3 plus 1. Okay, and now it's finally just a direct substitution problem. Plug in your 4, 1 over the square root of 4 minus 3 plus 1. 1 over 4 minus 3 is 1. The square root of 1 is 1 plus 1 is 2. So that limit is equal to a half. All right, next. So plug in 0, you get 1 half minus 1 half. That's a 0 on top. Plug in 0, 0 on bottom. So 0 over 0, we have more work to do. So this is called a complex fraction, fraction inside a fraction. So when you get complex fractions, you want to cancel out the smaller, smaller is not a good word, but the intermediate fraction. So you're not going to try to cancel out this x down here, but you do want to cancel out these denominators. So the way you cancel a denominator is by multiplying by the denominator. So we're going to multiply by a 2, which will cancel that 2 out. We're also going to multiply by an x plus 2, which will cancel that out. Whatever you multiply by on the top, you have to multiply by the same thing on the bottom. All right, so this will give us a new limit as x approaches 0. Forgot to circle my 0 there. All right, so we are going to distribute. Both of these distribute to this, and both of these distribute to that. Okay, so when I distribute to this fraction, the x plus 2's will cancel, and I get 2 times 1, which is 2. Then we have a minus sign. And when I distribute here, the 2's will cancel, and I have x plus 2. Make sure you put that in parentheses like that. Down here, nothing cancels out, just multiplies together. I'm going to put the 2 first, and then the x plus 2. All right, so now we're going to simplify the numerator, distribute my negative sign. So I end up with 2 minus 2, so the 2's cancel, and I end up with the limit as x approaches 0 of negative x divided by 2x times x plus 2. All right, one thing I haven't really mentioned yet with limit problems. Notice how every time I go to another step, I'm still writing that limit notation. That is required. Anytime you're working a limit problem that's not multiple choice, you want to make sure that you're writing the limit every single time. The point where you can stop writing the limit is the moment you actually plug that number in. So up here, see how I had the limit as x approaches 4, and then the next step I plugged the 4 in for x? That's when I can stop writing the limit. Okay, I've been doing that, but I haven't mentioned it yet. So that's what you need to do for your work. All right, we have one more algebra step here. We have an x on top, we have an x on bottom. That x and that x can cancel. And so we get the limit as x approaches 0 of negative 1 divided by 2 times x plus 2. Now we can plug our 0 in, negative 1 over 2 times 0 plus 2. So that's 2 times 2, which is 4. So my limit is equal to negative 1/4. All right, our next one, we have a difference of cubes, and they have this hint down here that we need to fill in. So this is how you factor a sum of cubes, a plus b times a squared minus ab plus b squared. And then a difference of cubes is very similar. It's a minus b times a squared plus ab plus b squared. Okay, the sign, the only thing that's different are the signs, and they follow an acronym, SOAP. Same sign, so you'll notice it's the same sign as the original problem. Opposite sign, opposite from that, and then always positive. And then you'll just notice the pattern of A, B going through there is the same for each one. Okay, so if we're going to apply this to this, we need to figure out what A and B are. So A and B are the uncubed versions, or the cube root versions of this. So for this, A equals x, B equals 3. 3 cubed is 27. All right, so we're doing the limit as x approaches 3. So if I plug it in, 3 cubed is 27, minus 27, that's 0. 3 minus 3 is 0. So it's a 0 over 0. We have more work to do. All right, so the limit as x approaches 3 of a minus b, so x minus 3, times x squared plus 3x plus 9. A squared, a times b, b squared. All right, on the bottom we have our x minus 3. So that works out really nicely. Our x minus 3's will cancel. And we have the limit as x approaches 3 of x squared plus 3x plus 9. Now we're plugging our number in. 3 squared plus 3 times 3 plus 9. So that's 9 plus 9 plus 9, which is 27. All right, these next two limits are actually very special limits. I'm not going to tell you what the name of them are, but they have a name. They're so special. But we can just do some algebra with these right now, so you can kind of start to get an idea of how these work, and then we'll talk about why they're special in a later lesson. All right, so this one has this delta x. Delta x is the variable in this problem. So this is the limit as delta x approaches 0. So if I plug in 0 for delta x, that would be x plus 0, which is just x. So that's 3x minus 3x, which is 0. Plug in 0 down here, you get 0. So it's a 0 over 0. We have more work to do. All right, this one's pretty simple. We just need to distribute the limit as delta x approaches 0 of 3x plus 3 delta x minus 3x divided by divided by delta x. All right, so we can see that our 3x's will cancel out. And so we have the limit as delta x approaches 0 of 3 delta x divided by delta x. And now your delta x's on the top and bottom can cancel. And so you have the limit as delta x approaches 0 of 3. And remember I told you the limit of a constant is equal to the constant. All right, last one. So this is actually in the same format. X plus delta x, x plus delta x. You have your delta x on the bottom. And then f of x is what that is, 3x. So this just had an actual function plugged in there. This gives it to you in function notation and then tells you what that function is out to the side. Okay, you can go ahead and figure out it's a 0 over 0 right now. If I plug in 0 for delta x, I end up with f of x minus f of x, which is 0, and a 0 on the bottom. Okay, so now we're going to rewrite this limit with our real function plugged in there. So the limit as delta x approaches 0 of 2 times x plus delta x. So that's what f of x plus delta x, that's what that means. Plug that in for x. So I need to put my minus 5 there. So there it is. Then minus f of x, which is this. So use parentheses because it's 2 terms, minus 2x minus 5, all over delta x. All right, we have some algebra to do. The limit as delta x approaches 0, distribute the 2x plus 2 delta x minus 5, and then distribute the negative, minus 2x plus 5, all over delta x. All right, what needs to happen on these for it to work and you to be able to solve it is anything that does not have a delta x attached to it has to cancel, because we need to be able to divide out this delta x. Otherwise, we're always going to have a 0 on the bottom, and you can't solve a problem with a 0 on the bottom. And it's going to be a 0 over 0 situation, which is really what we're trying to avoid here. All right, now if you've done everything right on these problems, then what I'm talking about will always happen. Everything will cancel out just like you need it to. So I have a 2x. See how this doesn't have a delta x attached to it? So I need to have a minus 2x up here to cancel it out, and I certainly do right there. Okay, this one has a delta x, so that's going to stay where it is for now. But this one doesn't, negative 5. And so I should have a positive 5 here somewhere to cancel out, and I do right there. So now I have the limit as delta x approaches 0 of 2 delta x divided by delta x. And now the delta x's, similar to the last problem, can cancel out. And just because I'm out of room, I'm not going to rewrite my limit again. But now I have the limit of a constant, which is equal to that constant. All right, that's how you do limits analytically. So hopefully you enjoyed that lesson, and I look forward to seeing you for the next one.